We'll start with section 6.2 in this lecture. We'll learn about finding the volumes. So here, when we have this volume plus disk, we also see finding the volumes of the washer. So here let S be the solid. This is solid, there's a typo, that lies between the planes P sub A and P sub B. So here is the plane P sub A and here is the plane P sub B. So we have a solid between these planes, which is represented by S. Assume that the cross sections of the solid is given by A and are perpendicular to this x-axis, which is this one. This is our A sub Ix if we consider one particular area A. And here we can represent the volume of this geometrical figure by V sub I. So here we have one small strip. Let me identify this strip here as the area A sub I and the width here as delta x sub I, which is also as delta x. Now our idea here is how do we find the volume? So here is the formula for finding the volume. Volume is area, which is represented by A sub I, times the width, which is delta x. So volume of the solid is given by capital V. This is not exactly equal to, so this is approximately summation A sub I times del x. So you're adding all the area times the width in the given geometrical figure. So when you sum up, you get the volume. Again, this is not exactly equal. You call it as an approximation symbol. And this delta x here, as this delta x grows smaller and smaller, we can say that delta x approaches 0. So one more way of representing the volume formula. So when we take the limiting condition, we take off this approximation symbol. So we use equality, but rather we write limit delta x go to 0. You write this as summation, no more sub I, but rather you write area AX times delta x, which means you're doing the limit for infinite number of strips, which is n. So there's one more way of writing this. The summation here can be rewritten as integration. So we will write this as integration x equal to a to b. Rewrite the limit and the summation as an integration x a to b. Area comes from the top. Bring this down. And this delta x here can be written as dx. Now this represents the cross sections are perpendicular to the x-axis. The dx variable tells you the cross sections are perpendicular to the x-axis, which we see here in this geometrical figure. Here is the x-axis and the cross section is perpendicular to the x-axis. Now let's do an example. So here we have a solid S that has a base which is a circular disk of radius 2. We want to find the volume of the solid if parallel cross sections take perpendicular to the base are squares. So first let's draw this circular disc with a radius 2. So let's mark the radius 2 here. This is positive 2 and these are negative 2. So this is any coordinate, say x comma y on this circular disc. As soon as I say this is the x comma y coordinate, we do understand that this distance here is x and this vertical distance here will be y. And if I ask you what is the distance between these 2 points, you know it is negative 2 to 2, which means you have, if you count the units, there is totally 4 units. Okay, you understand how to read this negative 2 to 2 units. Now, let's try to write an equation for the circular disc. Circular disc looks like a circle. So the equation is a typical circle equation, x square plus y square. The radius of the circle is 2, so I will be writing it as 2 square. Now we rewrite this, y square equals 4 minus x square. And in the problem, you're given that the parallel cross sections take perpendicular to the base, which means you define the variable dx here in the problem as the integral which is perpendicular to the x-axis. Now, you're also told that the parallel cross sections taken perpendicular to the base are squares. So here, the parallel cross section, if you consider a typical parallel cross section, let me use a different color. Say I'm going to use this light blue here. This is the parallel cross section. If you take such a typical parallel cross sections, each of these parallel cross sections will be a square of base 2y. Because when you calculate this distance here, this will be 2y. Hence the base, the width of the length and the width of the squares will be 2y. Whereas if you carefully observe, this distance here will be y. So this is the square base. So each of these cross sections will be a square base. Let's find the area of the square, length times width, which is 4y square. And let's try to replace the y square from here. Let's plug in the y square here to this variable. So we can rewrite this is 4 times 4 minus x square. Now we have a formula for area. We also know with what variable are we going to integrate. So here comes the volume formula. Integration, the lower limit. As soon as you write the dx variable, you read the x limits carefully for the problem on the x-axis, which is from negative 2 to 2. So write negative 2 to 2. As soon as you see dx variable, you have to understand the limits. What you write will be for the variable x. And then you have this ax dx. Dx is already there, so write ax where ax is the area. Now plug in the area, what you calculated on the top, which is 4 times 4 minus x squared, and then you have a dx. Now try to integrate this. Multiply this 4 for both of these numbers, so you get 16 minus 4x squared after you multiply. Now integrate the first term, you have 16x. Integrate the second term, you have 4x cubed divided by 3. So as soon as you finish integration, you're good to plug in the limits, negative 2 to 2. It's always upper limit first. So it is 16 times 2 minus 4 times 2 cubed divided by 3. So this is your upper limit minus the lower limit. So 16 times negative 2 minus 4 -2 cube divided by 3. So wherever you have the variable x, you plug in -2. And you simplify a little bit, and you see that you get the answer to be 128 divided by 3. So this is the volume of the solid if the parallel cross sections taken perpendicular to the base are squares. Let's move on to the next one. The solid S has a base that is bounded by the equations. The first equation is a parabolic equation, y equal to x square. And the second equation is a straight line equation, y equal to 4. Find the volume of the solid if the parallel cross sections are equilateral triangles that are perpendicular to the y-axis. So let's draw this. Let's draw a parabola y equal to x square. So this is the open upward parabola passing through the origin y equal to x square. Let's also draw this line y equal to 4, which is a line parallel to x-axis. And now let me mark a point here, say any coordinate on this curve as x comma y. You understand that this distance from here to here, this distance will be the x coordinate, and this will be your y coordinate if I say a coordinate as x comma y. You also know that this is y equal to 0 line, which is parallel to y equal to 4 line. And this is your y equal to 4 line. Now in this problem, you are asked to find the volume of the solid if parallel cross sections are equilateral triangle that are perpendicular to the y-axis. So here is the parallel cross sections you take. These parallel cross sections here are actually triangles. So let me draw the equilateral triangles. And they are perpendicular to the y-axis. So each of these lengths here will be 2x, 2x, 2x because they are the equilateral triangle. And then the height will be x. The height will be just the variable x. And each of the sides will be 2x. And for sure, this much distance is also x. I'm sorry, height is the unknown. This distance, the half of the base distance will be x. Height is still unknown. You're going to find it shortly. So let's do a Pythagoras theorem for this, for one of the right triangles. 2x, the square, equals h square plus the base, which is half of 2x, which is x square. So we rewrite h square equal to 4x square negative x square, which is 3x square. Now we take a square root. All we have is h equal to square root 3x. We neglect the negative sign of the height because height is positive. Now that we have the height, we should be able to calculate the area. But again, the question says the cross sections are perpendicular to the y-axis. So let's fix the integral here. dy is the integral what you want to take. This will be given in the question. You have to read and interpret it correctly. And this means the cross sections perpendicular to y-axis. Now we are good to write the area formula. which is half times the base 2x times the height square root 3x, which we found just now. Simplify, you have square root 3 and then an x square. And then you plug in for x square. Y is your x square. Y equal to x square. This is given for you. You're going to plug in. Now we have area as square root 3y. As soon as we have the area formula in the simplified expression, we are good to plug into this volume expression, y equal to 0 to 4, because you're going to integrate with dy limits and you take the y values. A dy, A is the area. So this is 0 to 4 square root 3y dy, and this is square root 3, and you have y square divided by 2 from 0 to 4. Plug in upper limit, plug in lower limit, subtract, simplify. You see that you get 8 times square root 3, which is the volume of the solid, where you have the parallel cross sections, which are equilateral triangles, and these parallel cross sections are perpendicular to the y-axis. The next one. Now let's consider rotating a region bounded between the x-axis and the function f of x. Read this x-axis carefully. And here is the function f of x. So here is the direction of rotation. You will rotate this region R between the x-axis and the function f of x from x equal to a all the way up to x equal to b. As soon as you rotate along this line, all you get is this cross section on the right. And the small piece here, we call it as a circular disc. So let's name the radius of this disc here, which is represented as y on the geometrical figure, r equal to y. But we know y is f of x, so I will name r equal to f of x for now. On the left, I'm going to name this point A here as P sub A. And on the right, I'll name this as P sub B. So this is the plane P sub A, P sub B. Now, let's also try to fix the variable of integration. Here in the problem, dx is the variable of integration. You have said that the region rotates between the x-axis and the function from x equal to a to b around x-axis. So you say dx is the integral cross sections perpendicular to, let me write in full words, perpendicular to x-axis. So now we write a equal to pi r square. It's a circular disk. So it's pi r square. Let's plug in for r. We have f of x and then a square. Now we are good to write the volume formula. Volume equals integration x equal to a to b. And then we have this a times dx, the area times the width. So again, this is from a to b. Area is pi times f of x square dx. And this was all about just calculating a general formula for the given problem, where we have done that. We calculated the volume when you have a small region which is rotated between the x-axis and the curve f of x. So the formula is pi times f of x square integration with respect to dx. And then after rotating the region, all you get is this cross section with a small circular disk of radius r. Now let's do some examples based on this discussion. So we are asked to find the volume of the solid obtained by rotating the region bounded by the following around the x-axis. As soon as you see the around the x-axis, these few words, you know that the variable of integration will be dx. And when you read the first curve, y equal to x squared plus 1, you know it's a parabola. You know x-axis, then you know x equal to -1 and 2 line. So let's try to trace all these 4 pieces on a graph. Y equal to x squared plus 1 parabola is shifted 1 unit on the top. So this is your y equal to x squared plus 1. If it is x squared, it passes through the origin. Now you also have bounding lines, which is x equal to -1 here and x equal to 2 here. And also x-axis. X-axis means y0 on all these points. That's this line. You can call it as x-axis, or you can call y equal to 0 line. Now you want to find the volume of the solid obtained by rotating the region bounded by the following around the x-axis. So if you try to draw a disk here, say this point here, this will be the direction of the rotation for the small disk what you consider. So now let's name the radius of this disk here as r equal to y. That's this distance is r equal to y. Now let's say r equal to y, and we know the area of the disk is pi r square, which is pi y square. Now let's try to plug in for y. For the given problem, we know this is the parabola x squared plus 1, and then you have the square. Now we are good to integrate, but you also want to note the x limits for the problem. It starts from -1 all the way up to 2. So these are the x limits. You write the volume formula, x equal to -1 to 2, then write area times dx. Area is x squared plus 1, then you have a square dx. But again, you also have a pi, so we should not miss that. So let me write pi here. Pi is a constant of integration. You can move this outside and FOIL this term, the square term, -1 to 2. So you have x to the 4, 2x squared plus 1, and then you have a dx. Now we are all set to integrate this integral. So let's do that. Pi times x to the 5 divided by 5, 2x cubed divided by 3, and then you have a positive x from -1 to 2. So do the upper limit minus the lower limit. Simplify. All you get is 78 pi divided by 5. Let's do one more example. Find the volume of the solid obtained by rotating the region bounded by the given curves around the y-axis. As soon as you see these few words around the y-axis, you know the integration, what you write finally, will have a variable dy. So you can write dy integral, the cross sections are perpendicular to the y-axis. You're also given the two curves, so let's try to draw them. The first one is a parabola, and the second one is a straight line, which is exactly your y-axis. So let's draw this parabolic curve. X equal to 4y minus y square. This is the curve which passes through the origin. So if you want to find the intersection points of this x equal to 0 y-axis and this given parabola, we have to solve the point of intersection. So all you do is, you have x equal to 0, plug this x equal to 0 in this equation, x equal to 4y minus y square. As you plug in, you see 4y minus y square equal to 0. And then you solve for solve for y. So y, just a minute. So you factor y, 4 minus y equal to 0. So either y equal to 0 or y equal to 4. So you have two values for y. So let me plot those values here. Y is 0 or y is 4. And suppose say this point is your x comma y. You understand that this is your x value and this will be your y value. Now we are asked to find the volume of the solid obtained by rotating the region bounded by the given curve around the y-axis. So you consider a small disk here whose radius is exactly x. So rename this. So this shaded region will be your solid. So write r equal to x. So area is pi r square, so pi x square. Plug in for x, it's 4y minus y square and then a square. Then we are all set to write the volume integral, which is y equal to 0 to 4 a times dy. So this is 0 to 4. A is pi x square. Sorry, we replaced x square by y term. So let me use the new y terms here. 4y minus y square, the square, and then you have a dy. So let's try to expand. FOIL this term. So it's pi times 16y square negative 8y cube positive y to the 4th, and then you have a dy 0 to 4. You integrate, apply the limit. So let me integrate it for you. This is 16y cube divided by 3, 8y to the 4 divided by 4, 5y to the 5 divided by 5. You have a pi multiplication outside. Now we are all set to apply the limits. The lower limit 0, upper limit 4. So you do a calculation for upper minus lower limit. And then check if you get the answer as 512 pi divided by